In this video, I'll be talking about Lab 3, where we looked at a bar magnet. The purpose of this lab is to use both experimental data and a computational model to find the magnetic field of a bar magnet at different locations. The data we glean from the experiment will be compared to the results from the computational model. The model will also visualize the bar magnet's magnetic field at different locations. We found that the magnitude of the magnetic field decreases with distance. We found the magnetic dipole moment of the magnet to be 2.29 am squared. The magnitude of the experimental magnetic field was 3.12 e to the negative 5 Tesla, while the model calculated a magnitude of 4.631 e to the negative 5 Tesla. Here are the physical principles we used. So we use this magnetic field equation in the code. We use the on-axis B field equation, mu naught over 4 pi times 2 mu over r cubed, and the perpendicular axis B field, which is 1/2 of that. We also use B equals kr to the n as another equation for the magnetic field of a bar magnet, which we converted into this equation on the bottom. The first magnetic field equation will be used in the computational model to calculate the magnetic field. The on-axis B field equation will be used alongside the bar magnet equation to find the magnetic dipole moment of the bar magnet based on the data we collected from our experiment. In our experiment, the system was the magnet and the surroundings was everything else. In our experiment, we used a magnometer app on the iPhone and made observations for the magnetic field for the bar magnet. First, we compensated for magnetic north by making sure the magnetic field of the bar magnet was orthogonal to the Earth's magnetic field so they could be measured separately. Then we found the location of the phone's magnometer chip. And then third, we observed the distance dependence of the magnetic field of a bar magnet. We found distances from the magnet that yielded specific B values, and this is shown in the figure on the top right. Finally, we measured the off-axis magnetic field. We got data on the magnetic field at a 45-degree angle from the magnet, and this is shown on the bottom right. When the magnometer is really far from the bar magnet, the magnetic field in the x direction is measured as near zero. And as the magnometer moves closer to the magnet, the x component of the magnetic field increases. Here are our experimental results for the on-axis data. So we got this graph, and from the equation listed here, we knew that n was the slope of the line, which equals negative 2.2994, and ln k is the y-intercept, which is negative 13.462. When we solve for k, we got 1.424 e to the negative 6. Using the B field on-axis equation to solve for the magnetic dipole moment, we got mu equals 2.29 am squared. Here are our off-axis results. So here's the magnetic field we got off-axis, and the magnitude was 3.124 e to the negative 5 Teslas, and the data also gave us a d value of around 0.198 meters. For our code worked by using a function, dipole B, to calculate the magnetic field at different positions R using the formula for B field given in the lab instructions. We looked at many different positions given by R, including 2 positions on axis, 4 positions on the perpendicular axis, and a position at 45-degree angle at distance d from the magnet. After the B vectors for each of these positions was calculated, arrows were modeled for each B field. Here are our initial conditions, with mu naught over pi being 1 e to the negative 7, mu mag from our experiment 2.289, and d perp being 0.14 from the experiment as well. And here are our results. So we got a B field at the 45 degrees, which magnitude was 4.631 e to the negative 5 Tesla. The blue arrow showed the B field perpendicular, the orange showed the B field on axis, and the pink arrow shows the B field on the off-axis position. In our experiment, we got a magnitude of the off-axis magnetic field to be 3.124 e to the negative 5, and the code got the magnitude to be 4.631 e to the negative 5 Tesla. So why are they different? There could have been potential sources of error. Other sources of the magnetic fields could have affected the experimental measurements, such as electronics. There could have been a magnometer error or an app error, or there could have been human error, so we could have made mistakes in taking distance measurements or overall inconsistencies in data collection. What if we did not orient the experiment to compensate for Earth's magnetic field? All of our observations would have been affected by Earth's magnetic field. The components which were supposed to be near zero would not be. Our calculated values will be much less accurate overall. What if the experiment were run again with 2 identical magnets end to end? The direction of the magnetic field would be the same, as the magnets are both on the same axis. We would expect the magnetic fields found in this experiment to be double that of the original experiment due to the principle of superposition.